Okay, let's dive right in. Here's something that might make you scratch your head a bit. Imagine an AI, right? It learns something like, my neighbor's dog is a golden retriever. Simple enough.
Seems straightforward, yeah.
But then what if you ask it, what kind of dog is my neighbor's golden retriever? You'd expect it to connect those, right? And
Oh,
say,
well,
the neighbor's dog.
you would, definitely.
But surprisingly often, even these really advanced AIs, they get tripped up on these like reversible relationships.
It's a known thing, too. People call it the reversal curse.
Exactly, the reversal curse. And it's not just some, minor quirk.
No, it points to something deeper,
Right, like a fundamental weakness in how these models actually understand relationships between things.
which really holds them back, you know? It affects their ability to reason, to make logical connections like we do.
It really does. It's a quite a fascinating disconnect.
Because these models, these large language models,
Yeah.
LLMs, I mean, they're incredible at so many things, generating text, translation, even writing code.
Totally. They're trained on just unbelievable amounts of data.
Exactly. So the fact they stumble on something so basic, like if A is related to B, then B must be related to A in the reverse, it really makes you wonder what's happening inside.
What's going on under the hood, yeah. And that's exactly what we're getting into today in this deep dive. We're going to try and unpack some really interesting research looking into why this reversal curse happens in LLMs.
And we're basing this on a specific paper.
Yeah, our main source is a recent paper called Is the Reversal Curse a Binding Problem? Uncovering Limitations of Transformers from a Basic Generalization Failure.
Okay. Binding problem. That sounds significant.
It is. But first, what really jumped out at me from the paper, like you said, is just the sheer amount of information these things see.
Right. Countless examples of relationships in text. Billions, trillions of words.
So you'd think they'd pick it up just through exposure.
You would, but this consistent failure, it really suggests it's not just about seeing more examples. It hints at a more fundamental limit in how they process it all, how they represent information internally.
Okay, so that brings us to the core idea in this paper. The researchers put forward this, well, I think it's a really compelling hypothesis.
It is.
They're suggesting this reversal curse might actually be linked to a problem that's, been kicked around for a long time in cognitive science, neuroscience, AI.
You mean the binding problem?
Exactly, the binding problem.
Yeah, that's a classic one. At its core, it's really about how systems, whether biological brains or artificial neural networks, manage to combine all the separate bits of information they get.
Into one unified concept.
Precisely. Think about, say, seeing a blue car. Your brain processes the blueness somewhere, the carness or shape somewhere else. Maybe the motion, too.
Right.
How do you actually perceive a single object, a blue car, instead of just separate features? That's the binding problem in a nutshell.
Okay, I think I get it. So applying that here, when an AI struggles with like, Tom's wife is Mary, therefore Mary's husband is Tom, it might be because it's having trouble binding Tom, Mary, and the wife-husband relationship together strongly enough.
Exactly, binding them in a way that lets it easily see the link from both directions.
It's like it doesn't quite lock down that Tom is the same. Tom, whether he's the husband or just, mentioned in relation to Mary. And same for Mary.
We've got it. And the paper goes deeper, suggesting two specific factors within the transformer architecture itself.
And transformers are the main technology behind most of today's big LLMs.
Correct. That's the engine. So the paper points to two potential issues in that engine causing this binding problem: inconsistency and entanglements.
Inconsistency and entanglements. Okay.
Yeah.
Sounds messy. What do they mean in AI terms?
Right. Let's break it down. Inconsistency first.
Okay.
The researchers think LLMs might struggle to keep a stable idea of the same thing when it shows up in different roles.
Different roles. Like subject versus object in a sentence.
Exactly. Imagine the model reads, John the doctor arrived. And later, we call the doctor John.
Okay.
It might not instantly robustly connect that the John in both cases is the same entity, just appearing in a different grammatical slot.
I see.
So back to our example. Tom Smith's wife is Mary Stone. The model forms representations, maybe Tom Smith as subject, Mary Stone as object.
Right.
Then it sees Mary Stone's husband is. It might struggle to strongly link the Mary Stone it sees now as the subject with the Mary Stone it saw before as the object.
Ah, so the connection isn't strong enough to easily retrieve Tom Smith for the prediction.
Precisely. The link between those different perspectives, those different roles, isn't quite solid enough.
Okay, that makes a lot of sense. It hasn't fully grasped the underlying identity across different contexts.
Yeah.
Now, entanglements, that sounds even trickier.
Yeah, entanglements. This
Oh,
is about how the model's internal codes for different concepts can get kind of mixed up during training.
mixed up.
Well, inside the model, concepts are represented numerically, right, as patterns. We call them embeddings.
Embeddings, right? Like coordinates in meaning space.
Sort of, yeah. And the model learns by adjusting these patterns based on the data it sees this process called gradient-based optimization.
Okay.
The trouble is, when the model updates the embedding for one concept, say Tom Smith, those adjustments can sometimes unintentionally nudge the embeddings of other concepts around.
Even unrelated ones.
Potentially, yes, especially if their names sound similar, or maybe they just tend to appear in similar sentences in the training data. Their internal representations can start to overlap or interfere.
So it struggles to keep the concepts truly distinct internally.
That's the idea. It's
Yeah.
like, imagine trying to keep track of two people named John Smith and John Smith.
Right, you might get them confused sometimes.
Exactly. Our brains usually figure it out from context. But inside the transformer, these overlapping activation patterns during learning might cause their underlying conceptual representations to become entangled, blurred together.
Which makes it harder to generalize relationships correctly.
Especially reversible ones, yeah.
Yeah.
If the core identities are a bit fuzzy or mixed, swapping their roles becomes much harder.
Wow, okay. So these like seemingly simple mistakes, they could actually be symptoms of really fundamental issues in how these powerful AIs represent the world.
It certainly looks that way.
But the paper didn't just diagnose the problem, did it? They mentioned some surprising findings, maybe ways forward.
They did. And one of the key discoveries was quite revealing, actually.
Oh, yeah. What was that?
They found that standard transformer architectures can learn reversal perfectly well,
They can. Wait, I thought the whole point was they struggle.
but only when they're operating directly on abstract concepts, on those numerical embeddings themselves without the messiness of surface-level language.
Hold on. So if you bypass the reading part, if you just give the AI abstract symbols like concept A, concept B, and relationship R as numerical embeddings.
It learns the reversal.
Yes. In their experiments, they set it up just like that. Each person, each relationship had its own unique learnable embedding, no actual names involved.
Yeah.
And the transformer models learned the A to B and B to A relationships with like near perfect accuracy. Wow, that's a real aha moment, isn't it?
It really is. It strongly suggests the basic transformer design isn't inherently broken for this task.
So the problem isn't the engine itself, but maybe the process of translating messy human language into those clean internal concepts.
That seems to be the crux of it, yes.
Yeah.
The failure really pops up when the model has to deal with and predict based on the actual words, the surface-level language.
Which brings us right back to inconsistency and entanglement.
Yeah.
The binding problem rears its head during that translation.
Exactly. It's about how language gets grounded into those concepts.
Okay, so if that language to concept step is the bottleneck, what did the researchers try? You mentioned a model based on JEPA.
Yes, JEPA. Joint-Embedding Predictive Architectures. It's an idea that's had success elsewhere, like in computer vision.
How does it work, basically?
The core idea of JEPA is to make predictions in an abstract space, not directly on the raw input.
Okay.
So the researchers adapted this. They created a kind of recognition module. Its job is to take the surface-level names, like Tom Smith, and map them to those abstract concept embeddings we talked about.
Got it. Translate the name to the internal code.
Right. And then the model tries to predict the next concept embedding in a sequence at that abstract level.
And how does it learn to do that mapping and prediction?
They used an approach called contrastive learning.
Contrastive learning rings a bell. How does that apply here?
Okay, so imagine the model sees Tom Smith's wife is. It needs to predict the correct concept embedding for Mary Stone.
Right.
At the same time, it sees the embeddings for, say, other people mentioned in the same training batch. Those act as negative examples.
Things it should not predict.
Exactly. The model learns by comparing the right answer with the wrong ones. It tries to pull its prediction closer to the correct embedding, Mary Stone, and push it further away from the incorrect ones.
So it forces the model to learn more distinct, less confusable representations for each concept.
That's the goal. Encouraging conceptual consistency and distinctness at that abstract level.
And the big question, did it work? Did this JEPA approach beat the reversal curse?
Well, remarkably, yes.
Really?
Yes, the researchers reported that this JEPA-based design, using that contrast of learning at the abstract concept level, importantly, they said it was, as far as they knew, the first time this had been achieved without resorting to common workarounds,
Workarounds
like manually adding lots of reversed examples to the training data, Mary Stone's husband is Tom Smith,
like.
or using special training methods that let the model peek at the sequence in both directions at once, which isn't really how these models are typically used.
So this was a more fundamental solution. That's huge.
It felt like a really significant step forward, yes.
I sense a but coming. You mentioned it wasn't quite a perfect fix.
That's right. While it was definitely promising, they noticed something interesting. As they made the GPM model deeper, adding more layers, more processing steps,
Yeah.
its performance on the reversal task started to dip again.
Oh, why would making it deeper hurt? Usually deeper is better, right?
Usually, yes. But this suggested that even with the contrastive learning pushing for consistency, those pesky entanglements we talked about,
They were still lurking.
they seemed to be. And maybe they became more problematic as the representations passed through more and more layers, getting more complex.
So even trying to keep concepts separate, they can still get tangled as the model gets more sophisticated, like signals crossing.
That seems to be the implication. So they tried to tackle the entanglements more directly.
How?
Well, one obvious thing was just making the model bigger, wider layers, more parameters. The hope was more space might let representations stay further apart.
Did that work? Just scaling up?
It helped a little bit, some minor improvements, but it wasn't, a game changer.
So throwing more compute at it wasn't the magic bullet.
Not really, no. The much bigger gains came when they tried something more targeted. They experimented with adding specialized memory layers into that initial recognition module.
Memory layers, what do they do?
These layers are specifically designed to create more discriminative activations. Basically, they actively work to push the internal representations of different concepts further apart.
Actively untangling them.
That's a good way to put it. Trying to ensure Tom Smith and Mary Stone have very distinct internal signals.
And that made a difference.
A significant difference, yes. Incorporating these memory layers, which directly targeted the separation of concepts, led to a substantial improvement in learning reversals.
Okay, wow.
It really seemed to highlight that you need to tackle both the inconsistency and the entanglement. Just focusing on one wasn't enough.
And did they find an optimal setup for these memory layers?
Interestingly, yeah. They found that with certain settings controlling how active the memory is, how sparsely connected it is, it could effectively create almost separate, unique embeddings for each concept.
Bringing it closer to that abstract setup where reversal was easy in the first place.
Exactly. It kind of bridges the gap between the messy language input and that ideal abstract representation.
This is really cool. So by tackling both consistency and entanglement, especially with these memory layers, they managed to overcome this really fundamental limitation, at least in their tests.
It certainly appears so, yeah. The evidence strongly suggests the reversal curse really is tied up with this binding problem in transformers.
Okay, so finding a way to reliably teach AI if A is B, then B is A is a big deal in itself. But the paper hinted this unlocks something more, right? More advanced reasoning.
Ah, yes. This is where it gets potentially even more exciting.
Lay it on me.
So the researchers showed that this ability to learn reversals seems to enable a new kind of internal knowledge use. They call it parametric forward chaining.
Parametric forward chaining. Okay, sounds technical. What's the core idea?
It means the model can implicitly connect facts stored within its own parameters, its own internal memory, chaining them together over multiple steps to deduce new information.
Okay. How does learning A is B means B is A enable that chain?
Let's take a simple maths example. Suppose the model knows x equals 5, y equals 3, and x plus y equals z.
Okay.
To figure out z equals 8 using this parametric chaining, it first needs to internally access the values for x and y, 5 and 3. Then it does the addition, 5 plus 3 equals 8.
Right.
But then, crucially, it needs to perform a reversal-like step. It might internally compute 8, but it needs to bind that value back to the variable z, going from an implicit 8 equals z to an explicit z equals 8 stored in its memory.
That recognition module and the reversal ability let it bind the result back to the correct variable name.
Exactly. And that binding, that recognition, is key. Because once z equals 8 is firmly established internally,
It can use that fact in the next step of reasoning.
Precisely. It creates a chain reaction of deductions, all happening within the model's parameters, bridging potentially large gaps in knowledge without needing to explicitly write everything down step by step.
That sounds potentially much more powerful and maybe efficient than how LLMs usually reason.
That's the implication. And they tested this. They set up some pretty complex arithmetic reasoning tasks.
Based on existing benchmarks.
Yeah, inspired by them. They had interconnected variables, all linked by addition. The model had to find the value of a target variable, maybe several steps away from the initial known values.
And they made it harder?
They increased the complexity, yeah. More variables, more connections, what they call the branching factor. Basically, more stuff for the model to keep track of internally.
Okay, so how did their JEPA model, the one with the memory layers that could handle reversals, how did it do compared to standard LLMs?
It did remarkably well. Significantly outperformed advanced LLMs on these tasks.
Better than models that use external knowledge retrieval and explicit step-by-step reasoning.
Yes. Those other models often rely on pulling in lots of facts from outside, non-parametric memory, or having the problem spelled out very explicitly in their input context.
And the performance gap changed with difficulty.
That was really interesting. As the problems got harder, the performance of the standard LLMs dropped off quite sharply. But their parametric memory model, the one good at reversals, its performance declined much more gracefully.
Suggesting it's better at handling that internal complexity.
It seems so. And as you'd expect, regular transformer models without these enhancements really struggled with these multi-step challenges.
Wow. That really drives home the potential here. It's not just fixing a little quirk. Overcoming the reversal curse might unlock a much deeper, more integrated way for AI to reason internally.
Exactly. This parametric forward chaining could be a more robust, maybe more efficient path towards complex reasoning, potentially getting past some limits of current approaches that lean heavily on external data retrieval.
Okay, so let's try and bring it all together for this deep dive. We started with this weirdly hard problem for LLMs, the reversal curse. If A is B, why is it so hard to know B is A?
Right. And we learned that, surprisingly, standard transformers can do it, but only in an abstract, non-linguistic setting.
The problem seems to pop up when translating human language into concepts, probably because of
Inconsistency and entanglements. The model struggles to keep concepts stable and distinct when represented through language. It's a form of the binding problem.
Then we looked at a potential solution, a JEPA-inspired model.
Using contrastive learning to enforce consistency, and crucially, adding specialized memory layers to actively fight entanglement.
And this approach showed real promise, breaking the curse without the usual workarounds.
Yes, a significant breakthrough in their experiments.
And finally, the really exciting part. Fixing the reversal problem seems to unlock a more powerful kind of internal reasoning.
Parametric forward chaining, allowing the model to connect facts stored in its memory, solve multi-step problems, and potentially outperform current methods on complex tasks like that arithmetic reasoning.
It really offers some valuable clues about a fundamental limit in current AI and points towards, well, potentially exciting new ways to build more capable models by focusing on better conceptual binding.
Couldn't agree more.
It does make you think, though, doesn't it? If something seemingly simple like the reversal curse runs this deep, affecting reasoning, well, what other basic limitations might be hiding in plain sight in today's AI?
Good question.
And what other maybe unexpected abilities could we unlock by tackling them? Perhaps thinking about this binding problem gives us a new lens to view other areas where AI struggles, like, true generalization or robust understanding.
It certainly opens up avenues for thought. And for anyone listening who wants to really get into the weeds on this,
Yeah.
the paper we've been discussing provides way more detail, obviously. Again, it's titled, Is the Reversal Curse a Binding Problem? Uncovering Limitations of Transformers from a Basic Generalization Failure. Definitely worth a read if you want the full technical picture.